Hey, I'm Calum,
And I'm Jan.
and this is our video on one-dimensional barrier scattering.
So I will first outline how we treat 1D scattering theoretically, then go through the rectangular potential barrier case, and introduce you to the phenomenon of resonance scattering.
And I'm going to take you through some applications that make use of the effects of quantum scattering, such as scanning tunneling microscopy, radioactive decay, and scattering's influence on some simple chemical reactions.
Right, so let's get started. So in this video, I will introduce you to some basic phenomena in 1D scattering and how we approach them in theory. The problem we're looking at here is what happens to a wave function, denoted psi I, that is incident on an arbitrary potential and is scattered by it. We'll be looking at the one-dimensional case because it's easier to treat analytically, but all the phenomena described here translate analogously to 2 or 3 dimensions. So diagrammatically, we have the position here on the x-axis and the potential here on the y-axis, and we have an arbitrarily shaped barrier, and there's an incoming wave packet incident from the left, part of which gets transmitted through the barrier, psi t, to the right, and a part of it gets reflected, that's psi r. Now naturally this separates our space into 3 dimensions. 1 and 3 are free space, and 2 is the potential barrier. Now the general way to approach this would be to find the eigenstates of region 2, the potential barrier. Knowing that, we can simply project our incoming wave packet onto these solutions, essentially finding out how does the incident state translate into the space within the barrier, into region 2. So this can then be propagated to time equals infinity using the Schrödinger equation, and that should in principle give us the reflected and transmitted parts. So the main outcomes of such a calculation would be the reflection and transmission coefficients, R and T. These simply tell us what fraction of the incident wave function is reflected and ends up traveling left, and which part is transmitted and ends up traveling right. Now we can in principle solve this problem for any 1D potential that has an exact solution. Now let us look at the case of a rectangular potential barrier. Realistically, we would like to work with an incident Gaussian wave packet, but it is very difficult to do the calculation in that case. We will instead be using plane waves, which can be seen as the limit of Gaussian wave packets with a high position uncertainty but a fixed momentum. So drawing this out, we usually denote the height of the barrier as V0 and its width as A. And again, we separate space into 3 regions. And for those 3 regions, we have wave-like solutions, written out here. And the wave-like solutions are composed of waves traveling left, which are given by the negative exponential sign here, and waves traveling right, which have the positive sign here. And the wave numbers of the waves are as follows. So these depend on mass of the particle m, the energy of the wave E, and the height of the barrier. Now, depending on the sign of K1, we have 2 different cases. If the energy of the wave is smaller than the barrier, we get exponential decay inside of the barrier. If the energy is larger than the barrier, the solution is still a wave propagating through. Now, to get on with the problem, we need to assert that there is a wave traveling from the left. This is done by simply setting the C prime coefficient to 0, since this describes a wave traveling to the left in region 3, and there should be no such thing if we have a wave incident from region 1. Right, and we also need to normalize the incident wave, so that's just by setting A equal to 1. Now we can get the transmission and reflection coefficients directly by interpreting our wave solutions. So since A prime describes the wave traveling left in region 1, its amplitude gives the reflection coefficient. And similarly, the amplitude of C gives transmission, because that's the wave traveling to the right in region 3. We also need to insert the conservation of probability, which simply says that R plus T must be equal to 1. So the reflected and transmitted amplitudes sum up to the incident amplitude. Now, if we put these together and assert that the wave function and its derivative must be continuous everywhere, we get out a system of equations that can be easily solved. For the E smaller than V0, which is the high barrier case, the transmission is given by this term. This is obviously a non-zero number, so unlike for the classical case, we get a finite tunneling probability, which increases for lower barriers and lighter particles. An important limit of this is very high barrier energy V0, in which case the hyperbolic sign here can be approximated by an exponential, so the transmission decreases exponentially with barrier width. This is the reason we can obtain excellent resolution in techniques like scanning tunneling microscopy, which Cal will be picking up on in the second half of this video. Now for E larger than V0, the low barrier case, transmission is given by this term. Again, even though the wave is above the barrier in energy, the transmission is not 1. So in contrast to the classical case, we see some reflection from the barrier. We can also observe another interesting effect. T now has this sign term in it, and we observe full transmission whenever this term disappears. Now this happens for some special values of k, which are given by integer multiples of pi over a here. Now these simply correspond to waves that fit exactly into our rectangular potential, like this. Now this is not a coincidence, but an example of resonance scattering, which occurs when the incident wave is too high in energy to be a bound state, but is instead a quasi-bound state of the potential. Now in resonance scattering, since the incident wave function is a quasi-bound state, it can be seen as slightly stable in the potential, which makes the scattering happen in a non-negligible time, essentially introducing a time delay to the whole process, during which some extra interaction of the potential and the incident wave function can happen. A well-known effect for this are the cross-sections in neutron scattering, which are highly important in the physics of nuclear fission. Classically, since the neutron and the atom do not interact, we would describe this with a hard sphere model. So since the atomic number Z should scale roughly as the volume of the nucleus, that is as the cube of the nuclear radius, and the collision cross-section should, in the hard sphere model, scale as the square of the nuclear radius, we would expect the collision cross-section to scale as the atomic number to the power of 2/3. So we would expect a plot of the collision cross-section against atomic number like that, a nice monotonous function. The experimental data, however, looks like that. It doesn't seem to follow any trend at all. This is a result of resonant effects in the scattering process, which cause some special neutron atom pairs to form quasi-bound states during the scattering and thus interact much more strongly. This is the reason behind the anomalously high cross-sections of some elements here.
Alright, so that was the theoretical bit.
And I'll take you through some of the applications now.
One of the most useful applications to come from quantum scattering is scanning tunneling microscopy, or STM. Here we'll show you a quick introduction to how STM makes use of this effect and what sort of results this technique provides. The STM technique was invented in 1982 by Gerd Bennig and Heinrich Rohrer, both of whom later won a Nobel Prize for this work. STM allows us to view the surface of a conducting sample in great detail, making use of the quantum tunneling and scattering of electrons. This means that it is not possible to explain how the technique works in a classical sense. The result of analysing a surface using STM is a very high-resolution image, where individual atoms are identifiable and any impurities are clearly visible. This makes it of great importance when trying to predict the surface properties of a new material or when attempting to make an atomically pure or flat sample.
When treating electrons in a quantum mechanical sense, we heard earlier how they are able to tunnel through a potential barrier. If we consider a metal in a vacuum, its surface can be described as a potential barrier of infinite width, and height equal to that of the work function of the metal. With nothing else in the vicinity, it is unlikely that any electrons will leave the surface. But if another conductor is placed in close proximity to the surface, it becomes possible for electrons to tunnel through the vacuum between them. We are then able to turn this into a complete electrical current by applying a bias voltage across the system forcing the electrons to tunnel in only one direction. The magnitude of this current, at constant voltage, is defined by the gap size A. This is how an STM functions. The main components of an STM can be easily described with a simple diagram. First, we have the tip, which does all the measuring from the STM itself, and the sample of whatever is being analysed. These are held at a separation A from each other. We then apply the bias voltage between the tip and the sample to ensure that the current flows in only one direction. During operation, the tip scans across the surface of the sample in all directions and records the current that flows through the system at all points. As the voltage is kept constant, the current that flows through the system is controlled by the width of the barrier, in this case the distance A. It is given by the equation here, where C is a constant related to the particular system, involving values such as the voltage that is applied. K is the attenuation constant, and in this case is very much simplified from where we saw it earlier, as we assume that the potential barrier is much higher than the energy of the electrons. As such, it is found with the equation here, where for metals, U minus E is equal to the work function of that specific metal. STM machines themselves are generally rather bulky, like this one here that takes up an entire corner of a lab. But they make up for this by providing incredibly high resolution images. We can work through a quick example here. As before, the current is proportional to e to the minus 2 Ka. If we consider a metal with a work function of 4 electron volts, it's easy to work out the attenuation constant for this system. Then the current is mainly defined by the width of the potential barrier, or the tip to sample distance. If we take A to be 10 angstroms, that gives an exponential factor on the order of 10 to the minus 9. Doubling this barrier width to only 20 angstroms will square this exponential factor, meaning that the current will become 1 billion times smaller. This is what gives the STM its incredible resolution, and what makes it such a powerful analytical technique. Here we have an example of an STM image. The target in this case is graphite, the structure of which is shown in the diagram on the right. Each of the individual carbon atoms in the honeycomb lattice is clearly visible, and yet in the hexagonal gaps the next layer cannot be seen even though it's only about 3 angstroms below the top layer. It's the ability to provide scientists with images like this that make STM so useful, and would not be possible without a good understanding of scattering and tunneling. Another example of quantum tunneling in action is with the radioactive emission of alpha particles from a nucleus. An alpha particle is a helium nucleus made up of 2 neutrons and 2 protons with an overall positive charge. Normally this particle would remain trapped within its parent nucleus. However, because of the quantum effects that govern the particle's motion, it may sometimes tunnel through this barrier and be emitted as radiation. Alpha particle emission can easily be described with a simple plot of potential energy against the particle's distance from the centre of the nucleus. Up until the radius of the nucleus itself, the strong force applies, meaning that the interaction is strongly attractive. After this point, the interaction is repulsive, governed by the Coulomb force between 2 positive bodies. Classically, the alpha particle would never be able to leave the nucleus. However, quantum mechanically, it has a non-zero probability of tunneling through the barrier and being emitted as radiation. We heard earlier that quantum scattering resonances involve the creation of a stationary metastable state. This has been well studied for photons and even some other elementary particles, but has more recently been observed to occur in chemical reactions. Here we will take a quick look at investigations into the effect that resonances have on one of the simplest families of chemical reactions. In this context, the H plus H2 reaction has been studied the most because of its simple nature. The full reaction mechanism yields no new products, but involves a substitution occurring between the single hydrogen and 1 hydrogen in the diatomic species. It is simpler to follow with a case involving deuterium, with that substitution shown on the right. The reaction comes into its own when computations are considered. Quantum mechanically, only the simplest of particles can be accurately defined, with errors and cost increasing dramatically with the complexity of the system. This is why this reaction family in particular is studied, as it is the simplest possible system while still using atoms. Classically, this system was of interest because of the timescale of the reaction, which could not be explained. The reaction's potential energy surface was shown to not have any local minima, yet it had an unduly long lifetime. More recent calculations showed that this extended lifetime may be caused by a short-lived, quasi-bound triatomic state, which is the result of resonances produced by the wave packets of the species involved. Here we have a figure from a review on the topic written in 2002. We have the reaction coordinate for 3 reactions from the H plus H2 family, each shown at 3 different vibrationally excited states. For reference, the minimum energy path, or MEP, is also shown on each of the 3 plots. We can see that the depth of the minima depend on the particles involved, as well as the vibrational state of the metastable species. The minima for the reactions involving deuterium are also visibly asymmetric because of the different reactant and product mass combinations. It is clear from these plots that the resonance and subsequently the metastable state is only present in the system at high enough collision energies. But the fact that it shows up at all in the plots means that quantum scattering resonances have a clear and visible effect in real chemical reactions. Further study of these phenomena could lead to the use of resonances to probe the properties of a reaction and provide a greater understanding of the molecular quasi-bound states that are formed. We hope that you found this video interesting. Thank you very much for watching.
Please stay tuned for Ewan and Will's video, which is coming up.